us about rakes.
Okay, I wasn't expecting that.
It's like the best title of the whole conference.
Yeah, you could say it's...
Okay, one rake to control them all. Is that what you expected?
Yes. Thank you for the introduction. The title is funny. I could give you a list of actual titles we had thought about. This is Chris's choice, so not my fault. But it's also not very informative, so I'm going to have to work out the explanations during the talk. Well, all right. We're going to talk about quantum circuits. Quantum circuits have been around for a few decades now. And, well, I hope I'm not going to be rude, but I'm going to explain what quantum circuits are. So you just append gates. You have a bunch of things that you can put next to each other. And you can also have several wires. The reason why I'm saying this is that one thing I want to focus on is this. So the hidden thing in quantum circuits is the tensor product, and it's the one important thing that we don't see in the picture. And well, it's something that now everyone uses, but do we understand quantum circuits that well? Well, we'll see. Maybe you understand quantum circuits better after my talk. So the first complete equational theory for quantum circuits for all unitaries came out in 2022. I should have listed the authors, sorry. Well, this is very recent. We could have expected something earlier if we actually understood quantum circuits that well. And actually this result came out thanks to completeness for optical circuits. And now, the other interesting thing, and which we're going to focus on, is that optical circuits are also circuits, but the hidden thing between the wires is a direct sum and not a tensor product. This makes it a lot easier to manipulate. And then, through this result, they were able to come up with an equational theory for quantum circuits. But that means that the heart of the result is here, and not for quantum circuits, let's say, natively. So here it is. I actually cheated because in the first paper they don't have one equational theory, it's scattered. So to put on the slides, I chose another. These are pretty usual equations. So you have phases that you can sum, you have h-gates that cancel. You have this triple C0 that makes a swap. This is, well, the Euler decomposition of the Hadamard gate. This is the general one. And then there is this mystical thing. It's necessary, but, well, now we have easier presentations for complete equational theory. But anyway, this is not really informative. What I'm going to try to get to by the end of the talk is why this is important, and I'm going to explain it through this, the diaxon. So in the original paper, the first paper for the complete equational theory, there is a distinction between structural equations and non-structural equations. And I'm going to quote the paper, because it's quite important. So these structural equations are structural in the sense that the transformations on the parameters are only based on the fact that R is an additive group. Did anyone understand that? Okay. In my case, I'm going to talk about structure in a slightly different way. I'm going to insist again on the direct sum. And in my sense, structural equations are equations that come up from the structure of the direct sum. And now, to see if you have a good, I don't know, intuition about these things, we're going to play a game. Okay, raise your hand if you think that this equation is structural. Okay, good. It is. So it is in the sense of the authors of the equational theory paper. It is also in my sense. Everyone happy? Okay. Raise your hand if you think this equation is structural. Okay. It is structural according to the other authors. It is not in my case. But it doesn't really matter. Raise your hand if you think this equation is structural. Okay, it is. How about this one? It is as well. Okay. How about this one? Fewer and fewer people. Well, it is. How about this one? So now I need to explain a bit because this is not such a usual gate. V is the square root of x. So v squared is the not gate. Is this structural? Haha, it's not. So this is in the early decomposition, and it's pretty much, in my sense, the only equation that is not structural. Well, now I've spoiled you. And how about this one? This one is quite interesting, and it is in both sense. This equation is well, basically how you use fewer controls in your circuits. So control is expensive in a sense, and if you want fewer controls, you can have more T gates instead. Okay, and my notion of structure is about the direct sum, but it is mostly about control. What you see on the circuits is control. Okay, I'm going to scroll through this quickly. So if you want to describe a unitary, you can do it by only describing it on the basis. And so this unitary here, for example, a C naught, you can describe it on the basis for 2 qubits, and you get this matrix. And the interesting thing to see here, but probably most people here are used to this, is that it is a block matrix. So here you have the identity, and here you have the NOT gates. And you can generalize this to all unitaries. So a controlled unitary is identity U. So, and this block matrix can be written as this. So identity O plus U. So the direct sum is hidden here when you write a control. And funnily enough, Z rotation gates are also of the same form. So you have the block identity and the block something. So you can write it as a control. And we're going to talk about all this mathematically. So we're going to do a bit of category theory, but in a very chill way. So a category is made up of objects and morphisms, and you can compose morphisms if they have the right type. And in our case, we're talking about circuits, so the objects is just the number of wires, and we call that a prop. And the number of wires can be summed, and in our case, if we talk about quantum circuits, the sum is actually interpreted as the tensor product. And if you talk about linear optics, it's the direct sum again. So there are several possibilities for the sum. And an important thing, and a very nice thing, is that a prop can be described by generators, and well, by generators and equations, like a group. Now I'm trying to make more sense of what is structural, give a proper definition of what kind of equations are structural. And based on this mathematical setting, I consider that structural should correspond to something that you can add, like literally a mathematical thing that you can add to your theory. And my point here is that control is going to be the answer. So the structure, the reason why some equations are structural is because they correspond to the addition of control to the theory. Okay, so start with any prop that you like. Well, not any. But let's say for circuits, so your generators are reversible, and you have a NOT gate, which is going to be important. Then for all morphisms in your category, you add its control, and its control of control, and its control of control. It is a very syntactic construction. For now, there's pretty much nothing about it. And then you quotient by all these equations. It is fairly easy to understand them. So the composition of control is the control of the composition. Control of the identity is the identity. Control behaves well with the tensor product. You can change the color of your control. So this control triggers on 1. This one triggers on 0. If you change the value, you change the color. If you have both colors, you trigger on 0 and on 1. So you basically just do the gate. If one triggers on 0 and the other triggers on 1, you can swap them. This thing, the swap. And also the control behaves well with the swap. Okay. A very recent paper by Simon Perdry and Noé Delorme came up with this equational theory for quantum circuits, which is much, much nicer than the one I presented in the introduction. And there is a line dividing structural equations and non-structural equations, kinda. And all this, as you can see, is about control, and is actually about, I forgot the word for it, conjugation. No? Anyway, you have two inverse gates surrounding another. And all this is about control, and I can show you that all those equations are derived from my theory. So if you have conjugation with control, I'm going to add in the middle, well, 0 controlled inverse of H and 0 controlled H. This one commutes over here. And since I have the inverse of H that triggers on 1 and on 0, it's just the inverse of H. And here I have H that triggers on 0 and on 1, so it's just H. So this is part of my equational theory. And now we can do this thing that we did syntactically, but mathematically. So again, if you start with a prop with a NOT gate and some generators, you build a completely new one. And now the generators have type 2 to the n, because we're not interested in the number of wires anymore. We're interested in the number of dimensions. And now this new prop will have a structure, not the tensor product, but the direct sum. So now the when we append wires, we'll write it with the direct sum. And we can do some magic. So the identity from the prop you started with transfers to the identity. Composition is composition. And then we can also translate the tensor product in this new setting. It's a bit disgusting, but this is simply a Kronecker product. So you can write. So this is a block matrix with a bunch of h's, and with the right swaps, and you compose with the same block matrix, you obtain the tensor product that you can define only with direct sums. And for now, we've just used the generators from the category you started with, and we're going to quotient with this thing. So our definition of the tensor product here doesn't force it to commute. So if you have a gate on one wire and a gate on another wire, they can the order doesn't matter. So you need to transfer it. Well, you need to force it. And the NOT gate is also needs to be forced to be the swap in this new category. And by quotienting by this, you obtain the new prop, and the main result is that this is, if you focus on objects that are power of 2, so just on qubits, this is exactly the same category that the one we had syntactically. So adding a control theory is literally the same thing as working with direct sums. So control is direct sum, full stop. A few examples. There is a nice paper about quantum theory with Z2. And this is the two generators that you need. This is a funny matrix. And if you want to define the prop, you have two generators that are x and j. And s squared is the identity, j to the third is the identity. And then you have jxj, which is x. And to this prop, you can add control the way I showed you, so either syntactically or mathematically. And finally, this is not complete yet. By just adding control, you need to quotient by a last equation, this one. I could find this thanks to some very nice work from Yves Lafont. Otherwise, I couldn't make it. And you can do the same for quantum circuits then. So now you generate everything with phases, z rotations, and some edge gates. And you define them. So this is what you can do at the 1 qubit level. You add control the way I showed you. And this is not complete yet. But if you quotient by this, it becomes complete. It's a bit funny. Okay. Right on time. So the one thing you need to remember is that control is exactly the direct sum. And in a sense that is very general. So all equations that are about control are exactly the mathematical interaction between the direct sum and the tensor product. So the fact that the tensor product distributes over the direct sum gives you all the equations around control. In category theory, this is called the rig structure, hence the title. And one of my points here is that if you want to design a programming language that manipulates these kind of things, maybe it would be better to have a type system with both tensor product and a direct sum to handle these matters. Or a nice way to introduce control, and Alex will talk to you about it later this week. Thank you.
So great talk. I really enjoyed it. I was wondering, so I'm now trying to go back to the examples that you gave and the things that you said were non-structural. And
do you want the? Oh yeah. This?
Yeah.
Okay.
So, firstly, can you walk through why HH is structural according to one interpretation and not the other now?
This is a great question. It's because of this, but I do not really understand it myself. But that's what's written in the paper, and they include the HH cancellation as structural because of this.
But it's not structural according to your definition because it can't be easily defined in terms of the direct sum?
Yeah.
Okay.
Thanks for the talk. My question is,
Thank you.
what's the relation of this to optical circuits? Because the reason that they use the direct sum in optical circuits is because there's this embedding of the unitaries on the complex numbers into the unitaries on L2 of R. So it's really like, in the representation you have the direct sum, which is like turned into the tensor product in infinite dimensional Hilbert spaces, so it's not a rig category. So is there some you can say about the optical circuits with your framework?
I'm not sure. Okay, wait. So the results. Well, first, the complete equation of theory is just for finite dimensional optical circuits. You have. I'm not such an expert on optical circuits, so you have, I think, many ways of representing them. So this one, well, the one I was talking about is based on the love calculus. I'm not sure that works with your what you just said about L2, but I guess we'll have to chat about it more deeply.
So I'm sorry, we are already late. The organizer is going to hit me on the head.